Hello and welcome to this lecture. So let me just quickly remind you what we saw in the previous lecture. We saw elimination as an important step in solving systems of linear equations. It's a very natural and important property, an important tool and trick that you have to use as you solve a system of linear equations. So here there are two equations and I showed you how when you can do an elimination step to get rid of one variable in one of the equations. So you end up in this triangular form and we know how to solve triangular form equations, right. So the idea once again is to take a general problem, break it down into a problem that you already know using some logical step. And notice this elimination step is very logical. See, if equation 1 is satisfied and equation 2 is satisfied, any combination like this is also satisfied. It's a valid equation. It's not a wrong equation, right. Equation 2 minus a2 by a1 into equation 1 is also a valid equation which will be satisfied because equation 2 is satisfied, equation 1 is satisfied. So the linear combination is also satisfied. So I'm using basic logic in combining these equations and getting rid of one of the variables. So I get it to the triangular form, and when I have the triangular form, I know how to solve. So always you go back, to with a more new problem, you go to a problem that you already know. Okay. So now it turns out, so we saw a whole bunch of examples. I'm not going to go through these examples once again. We saw different types of cases which they ended up. Okay. So this lecture is about this matrix vector view. So what we did so far can be conveniently captured in one simple matrix vector notation. And this notation is very powerful. It represents a lot of things and you can do many more interesting things with it. And most importantly, it is a door towards this very important area called linear algebra, which is a mathematical area and it's got wide applications in various places, and solving systems of linear equations is one application of linear algebra. But anyway, so let's just make a quick start at it. I'm not going to give you a very detailed lecture on matrices and vectors. It will take a long time. This is just a motivation to show you how systems of linear equations are related to matrices and vectors in a very direct, simple way. Okay. So when you look at this equation, a1x plus b1y equals c1 and a2x plus b2y equals c2, it turns out you can group the various variables here into vectors. Okay. And you can write it in that in this notation where I say a1 and a2 is one two-dimensional vector. There are two coordinates, so it becomes two-dimensional. And then b1 b2 is another vector, c1 c2 is another vector, xy itself is another vector. So you see all these vectors, and then these vectors are related through these linear combination in this equation. So that's that word linear combination is very important. It's a critical idea that connects these equations to the vectors. Okay. What is this linear combination? The vector a1 a2 is first scaled by x. You multiply by x on the right. So that basically is a1x a2x, right. So you write it conveniently as a1 a2 with x on the right. So vector itself is multiplied by x, and then plus b1 b2 multiplied by y. So what will that give you? You can see it will be a1x a2x b1y b2y. When I add the two vectors, what will happen? The corresponding coordinates will add. So you'll get a1x plus b1y, a2x plus b2y. On the right hand side, you just have c1 c2. Okay. So at one level, it's just a rewriting of that equation. There's nothing different I've done, but these vectors you can interpret them differently, and you can start doing very interesting things, and that's where linear algebra is born. Now, instead of writing this as two different vectors linearly combining, you can also write them together as a matrix vector product. Okay, so this multiplication a1 a2 times x, b1 b2 times y, you can further succinctly represent it as a matrix a1 a2 b1 b2, and then you put xy on this side. So you have the matrix a1 a2 b1 b2 and multiplying with xy. So that is best shorthand notation for x times a1 a2 plus y times b1 b2. Okay. So that is the famous matrix vector form for linear equations, and you will see most linear equations are written like this. You will write a matrix, then write a vector of unknowns equals a vector of constants on the right hand side. Okay. So it's just notation at this point. Why is this notation useful for us? It turns out this notation itself is useful to capture the elimination process. You can capture it in this notation in a very simple way. so that you don't waste too much space and all that. Okay. So a1x plus b1y equals c1, a2x plus b2y equals c2. That's your original equation. We know this matrix vector form of rewriting this equation, the same equation written in. So you can see clearly this one is already slightly simpler. No, all this plus and all is not there. Writing just the coefficients separately, the variables separately. It is just a notation. Okay, so nothing else is there at this point. So this elimination process was what? Instead of equation 2, we are going to replace it with equation 2 minus a2 by a1 into equation 1, of course assuming a1 is not 0. So you get two equations now, a1x plus b1y equals c1. The first equation remains as it is. The second equation becomes this modified form, right? It doesn't have x because we've eliminated x. It only has y, b2 minus b1 a2 by a1 into y equals c2 minus c1 a2 by a1. Okay, so that's the two equation. You can capture this also in the matrix form. Okay, so how do you conveniently do it? The row 2 of the matrix, the second row of the matrix is replaced with row 2 minus a2 by a1 into row 1. That's the idea. So when you do that, only the coefficient matrices x and y remain the same, right? The coefficient matrices are replaced by row 2 minus a2 by a1 into row 1. So you can just directly write it as a1 b1 0, b2 minus b1 a2 by a1, and then c1 c2 minus c1 a2 by a1. Okay, these are just convenient forms of bookkeeping in some sense, just keeping track of the coefficients, making sure you don't lose things. But this is very useful when the number of variables becomes large and all that. You don't want to be carrying around this x, y, z and all that, right? So you want only the coefficients matter. So you should just keep track of the coefficients, and the matrices give you a very convenient way of doing it. Not only this, you remember how I wrote the equation as linear combination of vectors. So it turns out solutions to linear equations can also be written as linear combinations of vectors. Okay, so that is a very crucial idea, and we will also express solutions in that form, and that you will see has very powerful connections as you go forward. So that connection is also important to motivate that connection. So far I've only shown you how you write the equation as matrix and how you can represent elimination on the matrix. We will use this later on, but more important than this is the fact that the solution to linear equations in many cases can be written as linear combinations of vectors. Okay, so let me motivate that with one very simple example. Let's take this really simple example where you have two variables and one equation, right? Basically this is a straight line, ax plus by equals c. The solution is all the points on the straight line. You can also write this in a very convenient form, assuming b is not 0. You can divide by b, you get y equals minus a by bx plus c by b, right? So you get a y equals mx plus b form, and you can write this as a linear, straight line. Slope is minus a by b, maybe negative, maybe positive, and then y intercept is c by b. Okay, so that's the solution, and that's your straight line. We know this already, right? It turns out this solution, this straight line, you can write it as a linear combination of two vectors. It's quite easy at some level, but I just want to impress upon you that straight line solutions for linear equations can be written as linear combinations of vectors. Okay, that's a very important point. You'll see that here. The points of the line are basically u comma minus a by b u plus c by b for every u in the real line, right? For every u in the real line, you simply put x equals u, you get the corresponding y, right? So you can maybe picture this real quick if you want to draw that, right? So you have a axis here, and then maybe I should do a different line. You have a straight line, and then for every u here, you're going to have a corresponding x. If you put as u, you're going to get a corresponding y, and that will be this guy, right? That's all is going on here, right? So x is u. Every u you have on the real line, you will get a corresponding y, that is minus a by b u plus c by b. Simple in some sense. Okay, so maybe I can keep this little picture on. Okay, maybe I should not. Okay, I'll take it off. Okay, so that's a simple picture. Now it turns out if you rewrite this as a vector, the points in the line, if I'm going to rewrite it as a vector, the x coordinate goes on top, right, u, and the y coordinate comes right below it, minus a by b u plus c by b. I can now write this as a linear combination or a sum of two vectors. What is the sum of two vectors? One vector is 0 c by b, the other vector is 1 minus a by b multiplied by u. Right? So, it is simple rewriting, I am not doing anything different here. I am taking u common out of the first term, I get 1 minus a by b plus what is left is 0 c by b. These two vectors are exactly the same, I multiply, I add, I rewrite. But you notice here, so the solution, the points on the line have been written as the sum of two vectors, right. The sum of two vectors here, these points, these two are the same, okay. These two are exactly the same. The points on the line are simply written as the sum of two vectors 0 c by b plus u times 1 minus a by b. As you vary u, you get all the points in the straight line. Okay. So, this is what is a very interesting connection, a very simple way to think about the straight line in this vector point of view. Okay. So, like I said, 0 c by b is one point on the line ax plus by equals c. Okay. So, you put x equals 0 and y equals c by b, you get that, right. So, you put x as 0 here and y maybe in another line. If you put y as c by b, you get this equation to be satisfied, isn't it. So, the 0 c by b is one point on the line ax plus by equals 0. What about this 1 minus a by b, right? What is this point, right? 0 c by b is on the straight line ax plus by equals c. What is this 1 minus a by b? It turns out this other vector u comma minus au by b is basically all the points on the line ax plus by equals 0. So, you can see that if you put x equals a, x equals u and y equals minus au by b, these two will cancel and you will get 0. So, all these points interestingly are on the straight line ax plus by equals 0. Okay. So, this is an important point to keep in mind. So, this all the points in ax plus by equals c can be written as one point in ax plus by equals c plus all points on another parallel line ax plus by equals 0, which goes through the origin, right. So, this ax plus by equals 0 passes through the origin. Why? Because 0 comma 0 is a valid point on that line. Okay. So, in summary, we are saying that the solutions to a linear equation, a simple linear equation ax plus by equals c, just one equation and two variables, can be written as one solution plus a line. Okay. That line is actually parallel to this line and it passes through the origin. Okay. So, this idea is very simple in this case, is very important as we go through and look at larger systems of linear equation. The solution for linear equations we will write in this form in many cases. You will see it will of course in a more extended version of this form, but this is the form that is important, and this is a very nice transition into the world of linear algebra later on when you see it. Okay. So, this is two variables, one equation, and a brief introduction to the matrix vector view of systems of linear equations. Armed with this, let us jump into slightly more complicated linear equations in the next lecture. Thank you very much.